All right, let's jump right into a really cool algorithmic puzzle. What if you were searching for a pattern in some text, but you had a superpower, the power to change letters on the fly? The real question is, how do you find that pattern using your power as little as possible? That's what we're tackling today. Let's get into it. So picture this. You've got this long ribbon of text, right? And your job is to find a specific, smaller pattern hidden inside it. But here's the twist. You've got a magic eraser. It lets you change a couple of letters. So what's the game? The game is to find the absolute shortest piece of that ribbon that has your pattern while using that magic eraser as sparingly as possible. That's the puzzle we're going to unpack. Okay, so here's how we're going to break this down. First, we'll lay out the puzzle officially. Then, we're going to make things easier on ourselves and solve a simpler case. After that, we'll bring back those transformation powers and talk strategy. We'll walk through a full example, and finally, we'll wrap it all up with the key takeaways and complexity. All right, section 1, let's get right to it and understand our core mission here. Okay, so let's break this down. There are a few key pieces here. We're looking for a substring of S, simple enough. But inside that substring, our pattern T has to exist as a subsequence. What does that mean? It just means the letters of T show up in the right order, but they don't have to be squished together. And here's the magic ingredient. We can make up to K changes to make it happen. The goal? Find the shortest and also the first alphabetically substring that pulls this off. All right, theory is great, but let's make this concrete with an example. So our big string, S, is ABCDDB. The little pattern we're hunting for, T, is just BDE, and our superpower K is set to 1. We get exactly one magic change. So we're trying to find BDE. Let's just, look at a piece of S. How about the substring BCDE? It's got a B and a D and an E. Hey, they're in the right order. But, that C is sitting right in the middle, kind of getting in the way. So as is, this doesn't work. It's not a valid window. But hang on a second. Remember our superpower? We have one transformation, K equals 1. So what if we use it on that pesky C? Let's just zap it and turn it into a D. Now our substring is BDD. And look at that. We can totally find BDE as a subsequence in there. We've got the first B, the new D, and the E. Perfect. That means BCDE is a valid window after all. Okay, that transformation power is pretty cool, right? But here's a classic programmer move. When you're faced with a tough problem, you simplify it first. So for a minute, let's pretend we don't have any magic powers. So what happens if K is 0? No magic eraser, no transformations. How does that change things? Well, the problem becomes a lot more straightforward, doesn't it? We're just looking for the shortest piece of S that contains T as a subsequence, plain and simple. It's a much more familiar place to start. And this really highlights the difference. You see on the left, when K is equal to 0, our goal is just finding T as is. It's a simple check. But on the right, when we have transformations, the goal changes. We're now doing a check plus a cost calculation. The logic gets more complex, but we get this awesome flexibility. We can basically recruit any character we want into our pattern as long as we're willing to pay the price. Okay, simplification was useful. But now it's time to bring the power back. Let's really dig into how K changes the game for our strategy. The best way to think about K is like having a pocket full of wildcard tokens. You get K of them. And anytime you need a specific letter for your pattern but don't have it, you can just spend a token and poof! You change the character you have into the character you need. So here's the bottom line. Let's say our pattern, T, needs a D next, but the character we're looking at in our main string, S, is a C. We're at a crossroads. We can either say, nope, not a match, and keep scanning for a real D later on, or we can spend one of our precious transformation tokens and just make that C into the D we need right now. That's the core decision. Okay, so how on earth do we actually build this? How do we search through everything efficiently and keep track of our transformation costs? Well, it's going to take a really clever combination of two powerful algorithmic techniques. And here it is, the secret sauce. The source material hints at it directly. Dynamic programming combined with a two-pointer sliding window. Think about it. The sliding window is perfect for efficiently looking at all the possible substrings. And dynamic programming, that's our memory. It's how we're going to remember the best ways we found to match parts of our pattern so we don't have to figure it out over and over again. It's the perfect team-up of efficiency and memory. So let's map this out into 4 basic steps. First, we scan. We'll use that sliding window to cruise through our main string S. Second, we remember. This is the DP part. We're going to keep notes on the best starting position we found for each part of our pattern T. Third, we calculate. For any given window, what's the transformation cost? How many tokens did we spend? And finally, step 4, update. If we find a valid window that's better, shorter, or the same length but comes earlier than our current best, we've got a new champion. Okay, that's the high-level strategy. It sounds pretty solid, but let's see it in action. Nothing makes sense like a good old-fashioned walkthrough. Let's trace our example. All right, let's follow the logic here in the table. We're at the start of S, at the A. We need a B to start our pattern, B, D, E, so A doesn't help. We move on. Okay, now our pointer in S is at B. Hey, that's the first character of T. We have a match. So we record that we found the start of our pattern at position 1 with 0 cost. Great. Next, our pointer moves to C. Now, what do we need for T? We need a D. Well, C is not D, but we can use our transformation. So we spend our 1 token, and you can see the cost for matching up to this point is now 1. Okay, moving on. Pointer's at D. We still need a D. Perfect. A natural match. Cost for this step is 0. And finally, the pointer lands on E. Our pattern T needs an E. Another perfect match. And with that, we've successfully found all the letters for B, D, E. The window we used was from the first B to this E, which is the substring B, C, D. And just like that, we found a valid solution. Now, of course, the full algorithm wouldn't stop there. It would keep searching to see if it could find an even better solution. But that little trace gives you the absolute core of how it works. So let's zoom out a bit. What are the big ideas we should take away from this whole puzzle? A few key insights here. First, and this is a big one, break down complex problems. Tackling the k=0 case first gave us a solid foundation to build on. Second, don't be intimidated by dynamic programming. At its heart, it's just a fancy way of saying remember what you've already figured out. It's all about avoiding duplicate work. Third, the sliding window is your best friend for efficiently checking all the substrings without wasting time. And finally, when a new constraint like k is added, it often just becomes another piece of information you need to track in your state. The core logic doesn't always have to change dramatically. And for all of you who care about performance, and you should, let's talk complexity. If we say the length of our main string S is n, the length of our pattern T is m, and our transformation budget is k, then the time this takes is roughly in the ballpark of n times m times k. The space or memory we need is proportional to m times k, mostly for that dynamic programming table we're building. You know, this core pattern, mixing an efficient search, like a sliding window, with a memory system, like DP, it's not just for this one problem. This is a real powerhouse combination that you see all over the place in computer science. So I'll leave you with this question to chew on. Where else could you use this? What other problems, maybe something like finding patterns in DNA, or even in advanced text editors, could be totally supercharged by this exact same strategy? Something to think about. Thanks for tuning in.